Welcome to lesson 4.2 on factors and primes. We're going to start with a definition of a prime number. Prime number is a number that has only two factors, one and itself. The smallest prime number is 2, then after 2 comes 3. 4 is not prime because you can multiply 1 times 4 and get 4, and you can multiply 2 times 2 and get 4, so it has more than two factors. Factors are numbers that are multiplied together to find a product. That's one way to define a factor. You can also define a factor as a number that divides evenly into a given number. So 3 is a factor of 12 because 3 goes into 12. It's a factor of 12 because 3 times 4 is 12. Composite numbers have more than two factors. 25 is a composite number. 5 times 5 is 25. 1 times 25 is 25. They can have a whole bunch of factors. See, 18 has 1, 2, 3, 6, 9, and 18. So multiple factors there. 0 and 1, just by definition, are not prime, and they're also not composite. And then the fundamental theory of arithmetic says that all composite numbers can be written as the product of prime numbers in only one way, and that's given. Like 18 can be written as a product of primes by saying it's 2 times 3 times 3, but you consider that to be the same as 3 times 3 times 2. The order doesn't matter. There's only one mixture of prime numbers that can be combined to make 18. So that's the fundamental theorem of arithmetic. So you might be saying, what good is all this? Well, you can use this if you want to reduce fractions. Also, this is really a lesson on arithmetic, by the way. It's pure arithmetic. There's not going to be any variables in this lesson, but it's really important that you understand the arithmetic part of it because it's going to be very helpful in some algebra that's coming up. So we're going to talk about how to do a factor tree and how to use repeated division to find the prime factorization of a number. So we have a number 54. Think about two numbers that you can multiply together to get 54 apart from 1 and 54. Obviously, there are some numbers that you can multiply together to get 54. If you think back to the first lesson, 4.1, on divisibility rules, and this is why we had that lesson, one of the main reasons is you can think about this as an even number, ends in 4, so you know you can go 2 times something, it would be 2 times 27. Also, you can do 5 plus 4 is 9, which demonstrates that 3 goes into this number as well as 9. So we could use 9 and 6. And it's kind of nice when you're doing factor trees to pick two numbers that are fairly close together if you can. Rather than doing 2 and 27, we can use 6 and 9. It'll get us done a little bit quicker with this factor tree method. So at every part of the factor tree, the product should multiply together to get the number that we're factoring, which is 54. 6 times 9 is 54. We're almost done here. What do you multiply together to get 6? 2 and 3. And then 9 would be, we put the times here too, 3 times 3. So there's, this would be 2 times 3 is 6, 6 times 3 is 18, and 18 times 3 is 54. And while I'm thinking of 54, I'm going to go ahead and do the repeated division method. So we put 54 under the division bracket. And when you think of a prime number that will go into 54, you have to have prime numbers when you're doing this division. So now's a good time to use 2. It's nice to use the small ones here. And then 2 and 7 make 9, so we know 3 goes into this number. I can't say 9 here because then I'm not using a prime number. I have to always divide by prime numbers. And 3 goes into 27 9 times. 3 goes into 9 3 times. And now I have the same list that I had when I used the factor tree. 2, 3, 3, and 3, and 2, 3, 3, and 3. Which is going to be 2 times 3 to the third power. If I write it using exponents, and this would be the same thing, 2 times 3 to the third power. Then I'm going to do 72. And again, I'm going to think two numbers that are as close together as I can get them, which would be 8 times 9 is 3. We know 9 works for 72 because 72 make 9. And you probably know that multiplication fact when you do that. 8 times 9 is 72. 8 is 2 times 4. And 9 is 3 times 3. Prime number, not prime number, prime and prime. So I'm almost done here. 2, and 4 becomes 2 times 2. And 3 times 3. And then times 3. So 72 would be 2 to the third power times 3 to the second power. And when I write it using exponential notation, usually the protocol is to write the smaller numbers first. So, I mean, there's nothing wrong with writing 3 to the second times 2 to the third, but you typically put the smaller number first. If I use repeated division here for 72, I always like to start with, if I can use 2, I'm going to use 2. 2 goes into 72, I use short division. 2 in the 7 3 times, remainder 1, and 2 in the 12 6 times. I'm going to use 2 again because I got another even number. 2 goes into 3 1 time, remainder 1, and 2 goes into 16 8 times. I'm going to keep using 2 as long as I can. 2 goes into 18 9 times. Now I have to use a 3, and 3 goes into 9 3 times. So, and as expected, I got 3 2s and 2 3s. So when would I use this? I could use this if I had to reduce a fraction, reduce 54 over 72, because now I'm looking for a way to find the greatest common factor of both of them. If I have 54 over 72, if I can find the largest number that goes into 54 and 72, that goes into both of them, I can use the equal fractions property, which says I can divide or multiply the numerator and denominator of a fraction by the same number and get an equal fraction. But the way that I can use prime factorizations to find the greatest common factor is to look for the prime factors that they have in common. Factors they have in common. Which means they both have to have it. So if I go back up to this list, I'll isolate this list right here, and this list right here. I see that there's a 2 in both lists. There's a 2, and here's a 2. There's no other 2's in 72, so I'm done with 2's. I can't use any more 2's because it only appears one time in 54. But I see I've got a 3 here in 54, and there's a 3 in the 72. There's another 3 in 54, and another 3 in 72. So I can't, even though I've got this other 3 here, I don't have any more in the 72. So I can only use the prime factors that they have in common. So I can use 1, 2, and 2 3's. I can use 1, 2, and 2 3's. And when I multiply those together, I get 18. And 18 would be the greatest common factor. So if I divide 54 by 18 and 72 by 18, I'm going to get, this will be 3, and it goes 4 times, and check math. Yep, 3/4. So 54 over 72 would equal 3/4 in lowest terms. Now I could have, let me put a little space here. Nothing wrong with just kind of trying to whittle these down. I can divide 54 and 72 by 2. And here I get 27 over 36. Then I can divide this by 3. And I get 9 over 12. And then I can divide by 3 again. And I get 3 over 4 finally done. Well, what did I just do? I divided by 2, and by 3, and by 3 again, which is the same as dividing by 18. So you can go a little bit at a time, but it's kind of nice to know how the theory works, how you can use greatest common factor and prime factorization to get the greatest common factor right off the bat. And that's going to be very helpful when you get into some algebraic stuff. I'm going to show you one more thing about this 54 over 72. Just another way to illustrate it. 54, we said, was 2 times, I forgot what I can figure it out here. 2 times 3 times 3 times 3, 9, yeah. 2 times 3 times 3 times 3, 74 was 2 times 2 times 2 times 3 times 3. Okay, another way I can do this is to just start canceling. I can cancel a 2 here and a 2 here. No more 2's. I can cancel a 3 here and a 3 here and a 3 here and a 3 here. And what's left is 3 over 2 times 2, 3 over 4. So, but that's still using prime factorization and go through the greatest common factor route, but it's kind of a nifty way to do that problem. We'll do one more example. We took 74 over 222, and these are kind of some numbers that aren't going to be real obvious what the greatest common factor is or how to reduce this. Although you can see, you could start by dividing by 2 because they're both even numbers. In fact, if I wanted to do a factor tree, not a factor tree, but repeated division, I could start with a 2 and 74 gives 3, remainder 1, 37. 37 is prime, so that's it. 74 equals 2 times 37. I'll use a factor tree for 222 just to review that process. I'm going to use 2 because it's not a real obvious one. It would be 111. And 111 kind of has the look of a prime number until you do the test for 3. 1 plus 1 plus 1 is 3. So 3 goes into 111. And if I did that, 3 goes into 11 3 times, remainder 2, and 3 goes into 21 7 times. So I get 2 times 3 times 37. Okay, so just to sum it up, 74 equals 2 times 37, 222 equals 2 times 3 times 37. So what do they have in common? A 2 and a 37. So the greatest common factor here is 74. Because 2 times 37 is 74. And I can tell by this, 74 is going to go into 222 3 times evenly. So if I want to reduce the fraction, I can divide by 74, and divide the denominator by 74, and I'm going to get 1 over 3. Just to prove it, 74 times 3, 12, 3 times 7, 21, plus 1 more. That's 222. So that one wasn't a real obvious one. So using the prime factorization, greatest common factor method, we're pretty good with that one. Okay, so that's the basic skills. You should be able to identify prime numbers and use either factor trees. Well, you should be able to do both factor trees or repeated division to find the prime factorization of a given number, and then use that to find the greatest common factor of 2 numbers, or more actually, 2 or more numbers, and then use that to reduce fractions. Just a quick list of generating some prime numbers. 2 is prime, 3 is prime, 5 is prime, 7 is prime, 9 is not, 10, 11, 13, 17 is prime, 19, 23, and then 29 is the next prime, 31, 4, 5, 6, 37. 39 looks prime. If you think about why it's not, what goes into 39? It's not even, so 2 doesn't work. Does it in 0 or 5? So 5 or 10 don't work. The digits add up to 12, so 9 doesn't go into 12, so 9 doesn't work, but 3 works. 3 goes into 12. So 3 would go into 39, 39 is not prime. And the next one is 41. These are the ones that you're going to use most often, like up through here, probably. But you do have to be able to recognize what prime numbers are. If you have a candidate, you're not sure if it's prime or not, like, think about your number 117. Looks like it might be prime, but again, if you do the test for divisibility, you'll soon discover it's not prime. You know 2 doesn't go into it, but 3 does, because 7, 1, 1 make 9, and 3 goes into 9. I wanted to add, there's something I did, this is the final thing I want to put in here today, which goes back to lesson 4.1, test for divisibility. If you have a rather large number, where the sum of the digits comes out to be a kind of a big number, I keep going here. Okay, 5,619,874. When you add the digits, you get 5 and 6 is 11, then 12, 21, 29, 36, and 40. I'm going to do that again because I did the sentence ahead of time. Just make sure I'm going to the reverse order here. So 4 and 7 make 11, and 8 is 19, 9 more is 28, 29, 35, and 40. Okay, is 3 going to 40? Well, you probably know the answer to that question, but you can actually take these 2 digits and break that down and do 4 plus 0 and get 4. And ask, does 3 go into 4? So you can just keep adding. If you get a 2-digit number, you can add those 2 digits when you're checking for divisibility for 3 and 9. Okay? Thanks.